These exercises are primarily for practice. It is assumed that you've already gone through some earlier PSVs and know the basics of drawing Lewis dot structures and then going on and applying VSEPR, which means we determine the molecule type, the number of bonding areas and non-bonding areas around the molecule, and therefore the molecular geometry. All right, now we'll turn our attention to the chlorate ion. We count up our total number of valence electrons. We see we have 26. That means 13 electron pairs. We look at our structure, and we're going to first connect up the outside atoms. Then we'll complete the octet of the outside atoms. That consumes 12 of our 13 electron pairs. We have 1 electron pair left, which will go on the chlorine atom and complete its octet. So all of our atoms have a complete octet. We note that our steric number is 4. There's 4 regions of electron density around the center atom. One of them is a non-bonding region. The other 3 are bonding. So it's of the type AX3E, which means our overall molecular geometry is trigonal pyramidal. We see that we have a total of 24 valence electrons and therefore 12 electron pair. Here's our skeletal structure. We'll start by connecting up the outside atoms, and then we complete the octet of all of the outside atoms. That uses 12 of our 12 electron pair, except currently nitrogen is electron deficient, so we need to make 1 double bond. It doesn't matter where we show the double bond, it's just between the nitrogen and one of these oxygen atoms. So we rewrite our Lewis dot structure. We see that all of our atoms have a complete octet. The whole thing has a net -1 charge. So this is a valid Lewis dot structure. We see our steric number is 3 because there's 3 regions of electron density around the center atom. All of these regions are bonding regions, so this is a molecule type AX3, and therefore our molecule is trigonal planar. Here we have the chloride ion. We count up our valence electrons. We see we have totally 20 total valence electrons, 10 electron pairs. We hook up the outside atoms in our skeletal structure, complete the octet of our outside atoms, and we see we've used 8 out of our 10 electron pair. The remaining 2 can go on the center atom. So now we have a complete octet on all of our atoms, and our Lewis structure is done. We see our steric number is 2 because there's 2 regions of electron density around the center atom. Both of them are bonding, so this is an AX2 molecule. Our molecular geometry is linear. This is the nitrite ion. We see we have 18 total valence electrons, 9 electron pairs. We hook up the outside atoms, complete the octet on the outside atoms, and we have 1 electron pair left over to put on the nitrogen. But the nitrogen currently is electron deficient. We need 1 multiple bond. So we rewrite the whole thing. This is our valid Lewis dot structure. We see all atoms have a complete octet, net charge -1. But for the geometry, we look at the steric number and the types of electron density. So our steric number is 3. There's 2 regions of bonding electrons, 1 of non-bonding. So it's AX2E. The result is a bent molecular geometry. Here's our water molecule, a total of 8 valence electrons, 4 electron pairs. We hook up our center atom, and then we have 2 lone pairs to put on the oxygen. All right, so here's our final Lewis dot structure. It's valid. All our atoms have a complete octet. Our steric number is 4 because we have 2 bonding regions, 2 non-bonding regions. And the molecules of a type AX2E2, which corresponds to a bent molecular geometry. Here's a hydronium ion. The positive charge here indicates that we've lost one electron, so we need to subtract one electron from our subtotal. So we have a total of 8 valence electrons, 4 electron pair. We hook up the outside atoms to the center atom. We've used 3 out of our 4 electron pair. The remaining one goes on oxygen, and we have a valid Lewis dot structure. Our steric number is 4. We have 4 regions of electron density around the center atom. It's of molecule type AX2E2, therefore trigonal pyramidal. Here's carbon dioxide, 16 valence electrons, 8 electron pairs. So we connect up the outside atoms, and we complete the octet of the outside atoms. At this point, we see that we need 2 multiple bonds. We can either have 2 double bonds or 1 triple bond. So here's our carbon dioxide molecule we drawn. It's a valid Lewis dot structure. All atoms have a complete octet. We see our steric number is 2. This is of the molecule type AX2. It's linear. Now I have a note here that we initially showed with 2 double bonds. Experimental evidence shows us this is how carbon dioxide bonds, but if we decided to put a triple bond on either side of this carbon, we would still have a valid Lewis dot structure, and the VSEPR result would be the same. And here's that alternative. If we drew CO2 with 1 triple bond rather than 2 double bonds, we'd still have a valid Lewis dot structure. The steric number would still be 2, and the result of our VSEPR analysis would be that CO2 is a linear molecule. So either of these results would have been acceptable. I simply chose this one first because I know that this is the way CO2 is thought to bond, consistent with experimental evidence.